All right, so in this video, we'll tackle how we can do all of our standard mathematical operations with radicals. So addition, subtraction, multiplication, and division. So we've already talked about these in the previous videos and in class, so I'm going to kind of give us a short version of this. Addition and subtraction, just like addition and subtraction always are about like terms. Multiplication and division are a little bit different. They have their nice rules, and they're the rules we've been using to simplify. So hopefully we already know them, but if we wanted to write down those rules formally, we have a product rule, and this is just something we should know, that the square root of a times the square root of b is equal to the square root of a times b. And we have a quotient rule. And our quotient rule tells us, since division is the other side of multiplication, if we divide two radicals, it's the same thing as a radical of that quotient. So the quotient of radicals is the same as the radical of a quotient. So those are our two rules. If you know a little bit more, just to give you a heads up about what a radical actually is, or how we can write it in a different way, these rules make a ton of sense. So here's where I'm going to tell you something I didn't tell you in class, because technically it's not part of the Math 92 curriculum. But it makes all of this stuff with radicals, I think, make a lot more sense. Turns out a radical is actually an exponent. So the square root of x, we can rewrite it as an exponent. This is x to the 1/2 power. Which makes sense because remember, the reason we have radicals in the first place, or square roots, is to undo squares. So if the square root of x squared is equal to x, well, it only makes sense that if we're talking about that, this is the same thing as the x squared raised to the 1/2 power, and then we could use the multiplication rule for powers, and this would just get us, this is x to the first power, which is just x. So if we think of our radicals as being exponents, this makes a ton more sense, because this is the same rule we saw back for exponents. X to the 1/2 times x to the 1/2, or we actually had it written in the other way when we did our exponents. We had this one, xy to the n is equal to x to the n, y to the n. Remember, if we had a product, we could break it up and distribute, so to speak, the n power to these two pieces. And the same thing is true as it was with radicals, that when we had, or with exponents, when we have x plus y raised to a power, you cannot do that same thing. You can't make this x squared plus y squared, because you need to be doing the FOIL, right, or the actual distribution. This is x plus y times x plus y, which has more complicated terms. So the same thing is true here. If you did something like this, you cannot split this up, because we're still looking at an exponent, and our exponent doesn't have any cool rule for addition or subtraction. So this is not x plus y. So that's that one big word of warning, and I sort of wanted to make sure, I mean, I know we didn't talk about it in class, but if we think of this as an exponent, realizing that's what it really is, it makes a lot of these rules make more sense, and us having to do a little bit less memorization. All right, so how would these rules work in practice? Well, let's see some examples. As we said in the simplify section, we could have something that looks like this. I don't know. In this case, it's not as simple as it can be, because it doesn't just have one radical symbol. So we would need to be able to go ahead and say, oh, sweet, I know that product rule. If I multiply radicals, I can just go ahead and multiply the radicands inside of a single radical. And if I'm clever here, I recognize that, oh crap, when we did this, we got a pair of 5s, right? So I can even rewrite this. This is the same thing as 25 times 3, which simplifies to 5 root 3. So there's my version. So that's using the product rule in this direction, right? So I'm going to write P in that direction. Technically, anytime we simplify, had this question started with the square root of 75, we could be using the product rule in the other direction. That's what simplification is all about. We could go, oh, well, this is just the square root of 25 times 3, which is, oh, here's my product rule in reverse, where I split it into 2. This is where it happened. And this is just 5 root 3. So we kind of use the product rule in forward and reverse in this previous example because we put them together and then we simplified after. Now the quotient rule, similar stuff. We saw one of these earlier. I gave you something that looked kind of like this. Change it up now. Now we're going to use the quotient rule in the reverse. So it's already presented as a single radical, but this particular example might be helpful if we actually look at it as two radicals. So we get the square root of 7 all over 3. And now this is simple enough because it doesn't have a fraction inside of a radical. So this was using the quotient rule in the reverse direction. Using the quotient rule in the forward direction, well, that would look like something like this. Let me think. 32 divided by the square root of 8. I have options here. I could go ahead and simplify these both first, but since I see two radicals divided, that could easily be combined into a single radical that might simplify a bit. My first step on this question would be to do this as 32 over 8. And then go, oh, great. 8 goes into 32 4 times. So this is just the square root of 4. Oh, and the square root of 4 is just 2. So we can sort of look and see what we're given. If we're given things as separate radicals, let's try combining them. If we're given things in a single radical that could be split up, let's try splitting them up and seeing if that helps. So that's most of the way we would use the multiplication and division. Now, getting into the addition and subtraction. Like I said, this is all about like terms. So if we have some simple example here, the square root of 2 plus the square root of 3 minus 5 square root of 2. Well, this particular example, we have some like terms, right? These root 2's are like terms. The root 3 is not a like term. It cannot combine with these. But we treat these just like these were x's or x squareds, right? Because this is 2 to the 1/2 power plus 3 to the 1/2 power minus 5 to the times 2 to the 1/2 power. So you can almost imagine these things, let me circle them with a different color, are like our x variable, right? They're our cat faces. So I'm going to turn these into my beautiful cat faces. So in this case, we have one beautiful cat face minus 5 beautiful cat faces. So we end up with -4 root 2. And then that root 3 cannot be combined in any way. It stays put. Now, where does this really get us in trouble the most? Let's give ourselves a big-ass warning. Here's when I see students make the most mistakes with these, especially in things like almost the quadratic formula would fall into this category. But if I gave students a thing like this, 3 minus 2 root 5, and asked students what to do, a lot of students would want to do, this is 1 root 5. Awesome. But the 3 and the 2 are not like, this 3, the two terms here, right, if we circled them, are not like terms. You cannot combine them. And the order of operations says we need to handle this multiplication before we can handle the subtraction. So this crap I wrote here is absolutely untrue, and it's a very common mistake. I have seen students in much higher level classes than Math 92 making that mistake. So this is actually as simple as it gets. We cannot combine this because we don't have like terms. So take that as a big word of caution. Now, as we saw in class, the other potential issue here or problem is that if we have something like, oh, I'm terrible at coming up with these off the top of my head, 3 square root of 2 plus square root of 8 plus, I don't know, 5 square root of 18. A question like this, we immediately look at and we go, oh crap, we can't simplify, they're not like terms. But as we talked about, and I know you guys know, what we need to do is a first step of simplifying. Ooh, that's not where I meant to write that. And by simplify, I mean these two can break down a little bit. 8 is 4 times 2, 18 is 9 times 2. If I see the perfect squares, I don't need to keep doing these little factor trees. I just know that I can break this into 2 square roots, right? So 3 root 2 cannot get any cleaner. But square root of 8 can be rewritten as 2 root 2. And the square root of 18, which is being multiplied by 5, can be rewritten as 3 root 2. So what we're really looking to do is 3 root 2 plus 2 root 2 plus 15 root 2. And now we can sum up all of those different things and find out that this is just 20 root 2. But your first step needs to be to simplify so you can see if there are like terms or not.